Standard retrieval-augmented generation pipelines have a strict structural ceiling. When tasked with complex, multi-document synthesis, the architecture breaks down entirely. Dense vector embeddings perform well in isolated tasks. If you need to search a single document for a specific semantic match, the system easily retrieves the correct paragraph. But when a query demands horizontal synthesis, pulling interconnected facts across distinct, separate documents, that same vector search mechanism fails. The most immediate symptom is the lost-in-the-middle phenomenon. As the context window expands to accommodate multiple documents, traditional RAG begins dropping the data located in the center of the prompt. Because the system relies on probabilistic vector matching, it also generates semantic drift and context collisions. The AI pulls in text that sounds mathematically similar, but belongs to an entirely different factual context. These are not software bugs that can be patched with a better prompt. They are strict mathematical limitations of mapping complex relational data into an isolated vector space. To achieve autonomous reasoning, AI architects have to move past dense vectors and adopt a completely different foundational data structure. FastMemory approaches this problem by discarding vectors entirely. It models context as deterministic interconnected nodes. This is the supremacy matrix, a benchmark comparing FastMemory against standard RAG. Look at the multi-document synthesis test. Standard RAG succeeds only 35.4% of the time. On the exact same evaluation, FastMemory achieves an 88.7% success rate using logic graphing. And on the finance bench test, it locally indexes dense documents with 100% accuracy in just 0.354 seconds. Because FastMemory is built with native C and Rust extensions, the entire process occurs on device. This guarantees complete data privacy without relying on cloud computation. Bridging the gap between 35% and 90% accuracy requires an entirely different engineering foundation. Surviving complex reasoning benchmarks requires a system built to mathematically preserve relationships rather than simply estimating semantic proximity. To understand why vector systems fail so drastically, we can examine the mechanics of the T-squared RAG bench table preservation test. The industry standard for preparing documents for a vector database is a process called naive chunking. When naive chunking encounters a structured financial table, it processes the data by slicing it into linear, disconnected text segments. This physical slicing permanently separates the data in the rows from their corresponding column headers. The system then creates a mathematical vector embedding for each of these newly disconnected chunks. The resulting vectors measure how similar the words are to one another. They cannot register the spatial layout of the original document. When an AI attempts to query this embedded table, it often retrieves the correct digits, but assigns them to the wrong fiscal quarters or categories because the structural map is gone. This precise mechanical breakdown is the root cause of standard RAG models hallucinating during table-to-text reasoning. This structural shattering also causes the system's low 22.1% score on the LexGlue benchmark, where complex legal clauses are split and their hierarchical context is lost. Any pipeline that attempts to force dense quantitative data into a linear vector space will inherently destroy the original context. FastMemory solves this spatial data loss through context-based function data events, or CBFDAE. Instead of relying on probabilistic guessing, this architecture performs a literal mathematical translation of the raw datasets. Instead of isolating data into detached chunks, the text and figures are mapped into precise topological nodes. This spatial mapping allows the topological nodes to perfectly preserve the original row and column layout of a financial table. Because every relationship is physically mapped within the structure, the system retains the absolute connections between all distinct data points. During retrieval, queries do not search a diffuse semantic cloud. They travel along exact logic graphs. This native topological design is exactly why FastMemory achieves greater than 95% accuracy on the T-squared RAG bench table preservation test. It is also the mechanism that allows the system to accurately route visual reasoning and chart data, scoring 91.2% in the FinRAG bench V evaluation. Topology provides a rigid, dependable memory structure. Standard RAG provides a fluid, approximate one. By treating data as an interconnected mathematical network, the architecture removes the AI's need to guess the surrounding context entirely. We can test this structural integrity directly against the frames dataset, which requires synthesizing information across 5 to 15 interrelated articles. Answering these prompts requires a workflow that successfully integrates overlapping specific facts drawn from multiple independent sources simultaneously. Standard API RAG systems face crippling latency during this multi-hop task due to the linear scaling of iterative payloads. Repeatedly querying the cloud results in latencies exceeding 2 seconds. FastMemory bypasses this, utilizing flat memory access, dynamically retrieving concurrent Wikipedia articles. This eliminates the network queue entirely, achieving a multi-document aggregation speed of roughly 0.38 seconds per query. This throughput processes thousands of tokens of dense context locally. It never relies on cloud integrations. Solving the multi-document bottleneck requires an architecture that executes natively and simultaneously, completely eliminating any cloud network transit. There are 2 fundamental philosophies of data retrieval. Vector matching is inherently probabilistic. It treats a close enough semantic similarity as a successful match. Deterministic topological nodes are exact and unyielding. Data points are either mathematically connected within the graph or they are not. In adversarial environments, probabilistic matching becomes a catastrophic liability. We can observe this in the Intel Red Team benchmark. Standard RAG scores 0. The final proofs of this architectural divide appear in the Biomix QA and CDAO benchmarks. Standard vector RAG fails medical logic queries due to unpredictable route failures, generating answers that risk severe HIPAA violations. Through deterministic, role-based synchronization, FastMemory maps the exact medical pathways to achieve a 100% success rate on Biomix QA. This flowchart demonstrates the CDAO benchmark for Department of Defense policy routing, where FastMemory uses air-gapped clustering to properly isolate instructions without context contamination. The ultimate advantage of this design is the generation of true, provable QA hits without any reliance on external black box models. Maintaining the standards of enterprise-grade reasoning forces a departure from the latency and security risks of iterative cloud embeddings. The next generation of enterprise AI will not be built on probabilistic guesses. It will be built on the unyielding mathematics of topological architecture.